All right, so today we're going to solve matrices. We're going to solve systems using matrices. So I'm going to take this 3 by 3 system and I'm going to turn it into a matrix equation. And in my matrix equation, I'm going to have a coefficient matrix. I'm going to multiply it by a variable matrix. And that is going to equal a constant matrix. So I'm going to show you how to build these 3 matrices, and then I'm going to demonstrate that these 3 matrices actually do equal the system that we're starting with. So your coefficient matrix, you just list all the coefficients. It does have to be a square matrix. When you solve 3 equation, 3 unknowns, you're going to have a 3 by 3 coefficient matrix. If you were going to solve 4 equations and 4 unknowns, you would have a 4 by 4. So you just look at the rows, coefficients, and they have to be in the same order, x, y, z. So the first row in my coefficient matrix is -4, -4, 3, followed by 2, -5, 0, because I'm missing the z term, and 2, -2, -3. So if any variables are missing, you need to put a 0 in their place. If I multiply this by a variable matrix, I'm going to list the 3 variables as a column in order. And then this would equal the constant matrix, -6, 28, and 22. Just to demonstrate that this is true, that I didn't just make this up, remember that when you multiply matrices together, you multiply rows by columns. So if I were going to multiply the first row by the variable matrix, it would be -4 times x plus -4 times y plus 3 times z. That would be the one on the left. And then you could go to the second row and multiply it times the variable matrix. And you would have 2x plus -5y plus 0z. And then finally, the third row would be 2 times x minus 2 times y minus 3 times z. And this would equal -6, 28, and 22. And when matrices are equal to each other, their individual entries or their corresponding entries have to be the same. So I hope that you recognize that this is the system. -4x minus 4y plus 3z would have to equal -6, and so forth. So once you've set this up, the easiest way to solve this system is to solve for x, y, z. So if I go back to the beginning where I defined these matrices, if you allow the coefficient matrix to be A and the constant matrix to be B, then when you solve for the variable matrix X, all you have to do is take A inverse times B. Now, I'm going to use a calculator. And so I'm going to go to my matrix menu. I'm going to edit matrix A. It is a 3 by 3. And I'm going to put in my coefficients. I'm then going to go back to my matrix menu because it automatically saves that in there. And I'm going to edit matrix B. And it's going to be 3 rows, 1 column. And it's just constants, -6, 28, and 22. And if everything works out perfectly, then all I have to do is go to my matrix menu, get the name of matrix A, inverse. I'm going to multiply it times matrix B, and I get 4, -4, -2. So that was my variable matrix X. And so I can think of this as X equals 4, Y equals -4, and Z equals -2. And I have solved that system. You could also write it as an ordered triple. You might see it both ways on an ACT or on the EOC. Now, not every problem has a solution. I want to look at one that, well, let's look at this one. I just want to write the system. Just to make sure that you understand where to put in your zeros. So my matrix, my variable matrix is going to be X, Y, and Z. It's going to equal my constant matrix, which is 12, 23, and 9. And then I want to make sure that in my coefficient matrix that my first column are X's, my second column are Y's, and my third column are Z's, so that when I multiply, my coefficients will match up with my variables. So the first row is going to be 5, 0, 1. My second row is going to be 4, 5, -2. And my third row is going to be 6, 0, 3. So that would be my matrix equation. Now, not every matrix equation that you set up is going to have a solution, just like every system doesn't have a solution. So if at any point you're solving for X, Y, and Z, if you get a square matrix that doesn't have an inverse, then that means either you've got infinitely many solutions or you've got no solutions. All right, so let's suppose that I made up this system that obviously does not have a solution, because X plus Y plus Z can't equal 3 different numbers. So if I try to set this matrix up, I'm going to have a coefficient matrix that's just all ones. It's going to be multiplied times X, Y, Z, and I'm going to get 2, 3, and 4. So if I put this in the calculator under matrix, if I look at that matrix A that I just filled in with a bunch of ones, if I try to take the inverse of that matrix, I'm going to get no inverse matrix exists. So that right there tells me that this problem does not have a unique solution. And if you look at the determinant of this matrix, and so I go over here and I get the determinant of matrix A, I'm going to get 0. All right, and so if the determinant is 0, then the inverse doesn't exist, and this problem has no unique solution. Now, you're going to have to be able to distinguish between no unique solution and infinitely many solutions. So if I move on to a simpler type of system, it should be obvious that in this system there is no there is no single solution because one equation is a multiple of the other. So every point that is on the line x plus y equals 4 is also on the same line 2x plus 2y equals 8. So when you set up this system of equations, the determinant is also 0. But in this case, it's not a no solution, it's an infinitely many solutions. So if one of your rows is a multiple of the other, then it's an infinitely many solution, not a no solution. So in class tomorrow, we'll work on taking systems. You might get a word problem, write your own system of equations, and then use matrices to solve it. So good luck.